Mount St. Helens is rumbling, with eruptions predicted 3 days in advance. The iconic Washington state volcano has been waking up since February, with hundreds of small earthquakes shaking the ground beneath it. This activity has captured the attention of geologists and volcanologists worldwide. What's causing this sudden surge in seismic activity? Is the volcano gearing up for another explosive event like its infamous 1980 eruption? In a race against time, scientists have made a groundbreaking discovery, a revolutionary technique that could predict a potential eruption up to 3 days in advance. But will this be enough to outsmart one of nature's most unpredictable forces? Could we be on the brink of witnessing another geological disaster? The answers might come sooner than we think. According to data from the Pacific Northwest Seismic Network, approximately 350 earthquakes have been detected beneath the iconic stratovolcano since early February. The majority of these tremors have been so minor that they went unnoticed by people in the area. Nearly 95% of the recorded earthquakes registered below magnitude 1 on the Richter scale. The most significant spike in activity occurred in early June when as many as 38 earthquakes were reported in a single week. These seismic events have been pinpointed to depths of around 3.2 miles below sea level, translating to roughly 4.6 miles beneath the volcano's crater. This increased seismicity, while notable, aligns with long-term patterns observed in volcanic systems like Mount St. Helens. Scientists at the USGS believe the recent activity is due to a natural geological process known as recharge. This occurs when fresh magma migrates upward from deeper within the Earth's crust, accumulating in reservoirs beneath a volcano. Recharge events are not unusual and have been observed in the past at Mount St. Helens, as well as at other active volcanoes around the world. In a recent update shared on X, formerly Twitter, the USGS explained the magma's journey. Mount St. Helens is fed by magma that forms near the base of the crust at depths of about 16 miles, the agency wrote. Over time, this magma slowly ascends through the lower crust and pools in a reservoir located 2.5 to 6 miles below sea level. Recharge events occur when magma enters this upper reservoir, increasing stress in the surrounding rock and triggering earthquakes. Although the current level of seismicity is higher than what has been observed in recent years, the USGS has emphasized that it is still considered within the background range for an active volcano like Mount St. Helens. Importantly, this activity does not signal that an eruption is imminent. Seismologist Seth Moran of the USGS elaborated during an interview with KO News, explaining that fluctuations in seismic activity are normal for Mount St. Helens. We've seen upticks like this before, and it's part of our understanding of an active volcanic system that there's ebbs and flows with seismicity. Overall, it's a reflection that Mount St. Helens geologically is a very active volcano. Mount St. Helens last erupted between 2004 and 2008, offering scientists a rare opportunity to closely monitor and study volcanic processes. The data gathered during that eruption significantly advanced the understanding of how magma systems operate and led to the development of more sophisticated monitoring tools. Moran recalled that in the days leading up to the 2004 eruption, scientists observed a dramatic escalation in seismic activity, with earthquakes occurring at a rate of 1 per minute. This intense activity sharply contrasts with the much lower frequency of earthquakes currently being recorded, underscoring the difference between normal background activity and signs of an impending eruption. Moran also discussed potential causes of the current seismicity. One explanation involves the influx of new magma into the mid to upper crust, naturally creating stress and triggering small earthquakes. Another possibility is that the entire volcanic system is pressurizing as leftover magma from the 1980 eruption continues to cool and release gases. This buildup of gas pressure could independently lead to increased seismic activity. Ultimately, if the pressure becomes significant enough, it might help push remaining magma out. Moran speculated that the 2004 eruption could have been triggered by a similar process, where residual magma from the 1980 eruption was released due to increasing pressure in the system. Adding to the interest in the region, another earthquake was reported near Morton, Washington. This tremor, which occurred just north of Mount St. Helens and west of Spirit Lake, was recorded at 7:52 a.m. on November 28 by the USGS. It originated at a depth of approximately 2.2 miles. While unrelated to the deeper activity beneath the volcano, such quakes highlight the tectonic complexity of the region. The social media account Earthquake Quake Alerts, which aggregates global seismic data from the USGS, reported a recent earthquake near Mount St. Helens with an initial magnitude of 2.3. The USGS subsequently revised its data, reporting the quake at a magnitude of 1.2. Despite this slight increase in seismic activity, the USGS has assured the public that there is no cause for alarm. The agency confirmed that the recent tremors have not altered the volcano's hazard profile, nor have they prompted changes to its monitoring systems, which track critical indicators such as ground deformation, gas emissions, or thermal activity. An eruption is not imminent, the USGS stated firmly. Mount St. Helens remains one of the most iconic volcanoes in the United States, primarily due to its devastating eruption on May 18, 1980. That event is remembered as the largest volcanic eruption in U.S. history, releasing an estimated 520 million tons of ash into the atmosphere. The eruption obliterated the surrounding landscape, sent towering clouds of ash high into the sky, and claimed 57 lives. Among the victims was David Johnston, a USGS scientist stationed at a monitoring site just 6 miles from the volcano. Johnston managed to issue a last-minute warning via radio, shouting, "Vancouver, Vancouver, this is it." Although the message did not reach its intended destination, it was intercepted and recorded by a ham radio operator, preserving his final moments. Today, Mount St. Helens is one of the most closely monitored volcanoes in the world, benefiting from advanced technology that tracks even the slightest geological changes. This vigilance has allowed scientists to detect the subtle, small-scale activity currently occurring beneath the mountain. USGS seismologist Seth Moran described the monitoring efforts as akin to placing a blood pressure cuff continuously on Mount St. Helens to track its pulse. These systems provide invaluable data, enabling scientists to identify any deviations in the volcano's behavior. Whenever there's any kind of deviation in that's when we really start paying attention and start asking ourselves what could happen, Moran explained. The USGS has linked the recent uptick in seismic activity to a natural geological process called recharge. This process occurs when magma moves upward from the deeper parts of the Earth's crust and accumulates in subsurface reservoirs beneath the volcano. Recharge is a well-documented phenomenon at Mount St. Helens and other active volcanoes worldwide. Importantly, such activity can continue for years without leading to an eruption. Moran elaborated on the challenges of studying volcanic systems, noting that scientists cannot directly observe what is happening deep within the Earth. Instead, they rely on indirect evidence such as earthquakes to interpret the situation. The earthquakes are the symptom, Moran explained. If you want to take this into the doctor's realm, the diagnosis is that this activity is consistent with a volcano that's recharging. Similarly, between mid-July and October of the previous year, Mount St. Helens experienced over 400 small earthquakes. Most of these tremors were below magnitude 1 and too weak to be felt at the surface. Such swarms of small earthquakes are not unprecedented at the volcano. Similar clusters of seismic activity occurred in the late 1980s and early 1990s, none of which directly resulted in an eruption. Mount St. Helens' history underscores the need for continuous monitoring. The 1980 eruption was not only catastrophic but also a wake-up call for volcanic hazard management. Since then, significant advancements have been made in monitoring technologies, including seismic networks, satellite-based ground deformation analysis, and gas detection systems. These tools enable scientists to build a detailed understanding of the volcano's dynamics and respond quickly to any signs of escalating activity. Despite the recent increase in seismicity, scientists remain confident that Mount St. Helens poses no immediate threat. The current activity is consistent with what has been observed during other periods of recharge and falls within the expected range for this geologically active region. The USGS continues to closely monitor Mount St. Helens, maintaining its role as a leader in volcanic research and hazard assessment. Through ongoing studies, scientists hope to gain even greater insights into the complex processes driving volcanic activity. This knowledge not only enhances public safety near Mount St. Helens but also improves understanding and preparedness for other active volcanoes around the world. In advance, could this be possible? Let's take a look at this. A team of physicists, geologists, and signal theorists from the University of Granada, Spain, has developed an innovative machine learning algorithm designed to predict volcanic eruptions, focusing specifically on Mount St. Helens. Their findings, published in the journal Frontiers in Earth Science, detail how the algorithm was constructed and tested using historical data from the volcano. By training the system to recognize patterns leading up to past eruptions, the researchers have made significant strides in advancing volcanic prediction technology. For decades, predicting when a volcano might erupt has been one of the most challenging tasks in geoscience. Scientists have installed sensors in and around active volcanoes to monitor seismic activity, gas emissions, ground deformation, and other potential warning signs. These instruments provide a wealth of data, but the ability to reliably predict eruptions remains elusive. One of the major challenges lies in the variability of volcanic systems. What signals an eruption at one volcano may have no relevance at another. This inconsistency has limited the effectiveness of generalized predictive models, leaving scientists with only a short window of a day or two to forecast eruptions with any confidence. To address these limitations, the research team took a focused approach by concentrating solely on Mount St. Helens. The researchers compiled an extensive dataset encompassing years of observations, including seismic and geological data recorded prior to and during the 1980 eruption. This dataset served as the foundation for training their machine learning algorithm. The system was designed to identify patterns that human researchers might overlook and incorporated advanced mathematical models to analyze earthquake signals. These models focused on key indicators, such as the buildup of pressure within the volcano and the energy stored in the system, which are critical precursors to eruptions. Once the algorithm was trained using data from several historical eruptions, it was tested on past events to evaluate its predictive accuracy. Remarkably, the algorithm demonstrated a 95% success rate in predicting eruptions at least 3 days in advance. This level of accuracy marks a significant improvement over traditional methods, which typically provide little more than a 1 or 2 day warning window, if any. The significance of this research lies not only in its scientific rigor but also in its potential applications. A reliable prediction tool for Mount St. Helens could greatly enhance public safety by providing earlier warnings of an impending eruption, allowing more time for evacuation and preparation. It could also serve as a model for developing similar tools for other active volcanoes around the world. This breakthrough comes at a critical time, as monitoring teams have recently reported signs of increased activity at Mount St. Helens. These observations include subtle but notable changes in seismicity, gas emissions, and other indicators that could suggest the volcano is entering a more active phase. While such activity does not necessarily indicate an imminent eruption, it underscores the importance of continuous monitoring and the need for advanced predictive tools like the one developed by the University of Granada team. The study highlights the importance of machine learning in geoscience. By automating the analysis of large datasets, these algorithms can uncover patterns and correlations that might otherwise go unnoticed. In the case of Mount St. Helens, the algorithm's success demonstrates the potential for this technology to revolutionize how scientists approach volcanic prediction. Looking ahead, the team's work could pave the way for broader applications of machine learning in volcanic monitoring. With continued refinement, similar algorithms could be adapted to study other volcanoes, providing earlier and more reliable warnings of eruptions. The ultimate goal is to improve public safety and minimize the impact of these natural disasters by providing communities with the information they need to respond effectively. If Mount St. Helens erupts, could it be as explosive as the 1980 eruption? Even though the height of the volcano has decreased since then, Mount St. Helens retains the potential to produce an eruption as explosive as the catastrophic 1980 event. Despite the significant reduction in its size since that time, the explosiveness of a volcanic eruption is not determined by the volcano's height or size but rather by key factors such as the composition and viscosity of the magma, the content of dissolved gases, the buildup of pressure within the magma chamber, and the overall structure of the volcanic system. Mount St. Helens is well known for its production of andesitic and dacitic magma, which is rich in silica and characterized by high viscosity. This viscous magma traps gases as it rises toward the surface, allowing pressure to accumulate. When this pressure is released suddenly, it triggers a violent eruption. The devastating 1980 eruption is a prime example of this process. The eruption occurred because the system became highly pressurized, resulting in the explosive release of energy that devastated the surrounding landscape. If similar conditions arise in the future, Mount St. Helens could produce an eruption of comparable magnitude. The 1980 eruption marked a turning point in the history of Mount St. Helens. Before the event, the volcano stood at an elevation of approximately 9,677 feet, making it one of the most prominent peaks in the Cascade Range. However, the eruption began with a massive landslide, the largest in recorded history, which removed the northern flank of the mountain. This landslide reduced the height of Mount St. Helens by about 1,300 feet and left behind a vast crater that is now a defining feature of the volcano. The summit collapse exposed the internal volcanic conduit and fundamentally altered the volcano's structure, reducing its height to the current elevation of approximately 8,363 feet. Despite this reduction in size, Mount St. Helens remains an active and formidable volcanic system. Beneath the surface, The volcano is fed by magma reservoirs located at depths of 2.5 to 6 miles below sea level. These reservoirs are periodically replenished in a process known as magma recharge, during which new magma enters the system and builds pressure. Scientists monitoring the volcano have detected ongoing signs of magma recharge, indicating that Mount St. Helens is still capable of generating powerful eruptions. The structural changes caused by the 1980 eruption, including the creation of the crater, may have made it easier for magma to ascend to the surface. While the weakened structure supports smaller dome-building eruptions, it also increases the likelihood of explosive events if the system becomes excessively pressurized or if the volcanic dome collapses. The gas content of the magma is another critical factor that contributes to the volcano's explosive potential. Magma at Mount St. Helens is rich in dissolved gases, such as water vapor, carbon dioxide, and sulfur dioxide. As magma rises to the surface, the decrease in pressure allows these gases to expand and escape. If this process happens rapidly, it can lead to explosive eruptions. The volcano's history shows that these conditions have occurred multiple times, with significant eruptions documented over the past 10,000 years. The 1980 eruption was particularly catastrophic, but Mount St. Helens' geologic record demonstrates that such events are part of its natural eruptive cycle. Smaller dome-building eruptions occurred between 2004 and 2008, during which lava slowly emerged from the crater to form a new volcanic dome. These events provided further evidence of Mount St. Helens' ongoing activity and dynamic system. While these eruptions were less dramatic than the 1980 event, they underscored the fact that the volcano remains highly active. The history of Mount St. Helens suggests that significant eruptions often occur in cycles separated by decades or even centuries. While no major eruption appears imminent based on current monitoring data, changes in seismic activity, ground deformation, or gas emissions could signal an approaching event. The reduction in Mount St. Helens' size since the 1980 eruption does not diminish its explosive potential. What matters most are the processes occurring beneath the surface, such as magma recharge, gas accumulation, and pressure buildup within the magma chamber. If conditions similar to those of 1980 develop again, Mount St. Helens could produce another eruption of equal or even greater explosiveness. Scientists are closely monitoring the volcano using advanced technology to detect early warning signs of any changes in its behavior. Although the timeline for the next major eruption remains uncertain, Mount St. Helens continues to be one of the most active and closely watched volcanoes in the world, a stark reminder of the dynamic and potentially dangerous nature of the Earth's geologic processes. And finally, could the eruption of Mount St. Helens trigger eruptions in nearby volcanoes? The potential for an eruption at Mount St. Helens to trigger eruptions in other nearby volcanoes within the Cascade Range is a complex and uncertain process. Remember to stay informed and subscribe to our channel for more updates on this dynamic volcanic landscape and other geological phenomena. Thanks for watching and stay curious about the wonders of our planet.